So the goal of this lecture is to present two approaches to solve QuTalent problem or optimization problems with classical solvers. Okay, I will present first an exact approach, and then an heuristic approach that will be basically the simulated annealing. So let's start for this the exact approach. So let's remember. So we have a cost function that depends on some binary string. Okay, this is a binary. And we usually want the goal is to minimize. The problem we're going to solve is to minimize over all the possible bit strings this cost function. Okay, and so the naive exact approach would be just to consider all the possible bit strings and evaluate this function and find the minimum, so find the x that attains the limit. Okay. Usually to do this is a valid approach. Actually, for small problems, it's the easiest thing that you can do. In case that the size of the process is not very large, so just it's the easiest way to program this. And so one could think of this about a tree, right? We could start as the first bit. So the first bit would take value 0 or value 1. And then if the first bit takes value 0, we could substitute in our Q expression the x1 by 0. And we would get a second expression that we could evaluate, right? And we could evaluate the second bit. The second bit would take value 0 or 1. The same here. And so on and so forth. We could explore all the three possibilities. And at the end, we will get some results. Actually, 2 to the n possible outcomes, and we will see which one is the smallest. Okay. Although this approach, as I was saying, is very rudimentary, it's in some situations can work. The next most sophisticated thing that you could do is to understand some bounds on these quantities. So imagine that if you get expressions, so as we said, when you progress on this tree, you continue getting simplified expressions for this formula. And maybe it's easier if I put an example. Let's consider a problem for n equal to 3. And let's consider a QO formula. So this will depend on 3 variables, x1, x2, x3. That will be the following, I don't know, 2 times x1 times x1, x2 plus 3x to x3 minus 7 x1 x3 plus x1 and so on. Okay, let's consider the expression. So one thing that is when we evaluate the first variable x1, so this expression simplifies a lot. So here the expression that we get is even more simple, right? So after considering c of 0, x1, x3, we see that this expression just simplifies to, if it takes the value 0, x1, only this term here survives. So in the rest of this tree, we should only use this simple expression. But there is also another thing, is that this expression, we know that this is lower bounded and upper bounded by, so this is, let's say that this expression here, if you want, if we're interested in minimizing, we know that this is lower bounded by 0. So this idea of combining the tree structure with bounds on certain branches is when we use these two concepts, you say that you are doing the branch and bound methods. Okay, branch and bound algorithm. And the advantage of this algorithm is that it's exact. So you will find the optimal solution. The disadvantage is that if the problem size is big, then you have so many possibilities that even if you bounce some branches, anyway, it takes a long time. Okay, so I would say that in practical situations, you will only use exact methods like the branch and bound if the problem is relatively small. But if not, you in general, you will not have enough computational power. And what you do is that you use the so-called heuristic approaches. And the heuristic approach that I would like to present here is the simulated annealing, because it has a technique widely used in statistical mechanics and applied in many problems in many real situations. So we say that an approach is heuristic when instead of, let's assume that we have here our space of all the possible solutions. Okay. In our case, it will be the set of all the binary strings of length n. So we have 2 to the n elements in here. And we say that an approach is exact when we kind of perform an exhaustive search on all the possible space of solutions. Okay. In contrast, we say that an approach is heuristic when instead of performing an exhaustive search, we just navigate, explore this space of solution with some criteria. Okay. There are several heuristic approaches. One very popular one is the genetic algorithms, in which you just recombine parts of different solutions. You just cut and join different bit strings from different solutions and emulate a kind of biological evolution. Okay, but in this course, I will present an also very popular approach that is the simulated annealing. So how the simulated annealing works? The idea is the simulation of an annealing process of a system that is very hot and it's being cooled down. So we have this set of solutions that in our case are just bit strings, right? And the idea is that we start with some bit string, randomly chosen, a random sequence from 0 and 1. And then we propose a random change of this bit string. So we propose a new x prime that has been constructed from some previous x. Okay, I will explain the essential idea of the method. There are, in practice, when you program it, there are several ways. So, for instance, an elementary change from some x to some x prime could be just flipping a bit of the system, but we could decide to flip 3 bits or whatever. Okay, these bits depend on the situation, etc. So the first step is that we propose a change, and then we need to, so we are in some point in our state of solution, we propose a change, and the acceptance or rejection of this change will depend on how favorable for the system is the energetically speaking. So our cost function, we have a cost function. Okay, maybe in this example of the usually people use energy for expansion in the sense that you have some so Hamiltonian, for instance, and different configurations for this Hamiltonian, and you would like to find the configuration of minimum energy, so the ground state of your system. And then here the analogy with the annealing comes from the fact that we will imagine that we are gradually cooling down our system. But let me be more specific. So we have this cost function, and we have to decide if we accept or reject the change. Okay, so here we have two options. The question is, do I go from x to x prime? Should I go from x to x prime? Or, in contrast, I should just remain in x. No, I have these two possibilities. Either accept the change and go to x prime, so explore the configuration space to that direction, towards the x prime, or just remain in x. So we use a function that is called acceptance probability function. That is some function t that in which we usually compare the energies. So basically, we compute the energy or the value of the cost function. So let's say E prime and E, where E prime is the energy of the configuration x prime and E is the energy of x. So basically, the method so when you program it, you need to decide which acceptance probability function you take. Usually, the most standard thing is that to take this function as only depending on the energy difference, A prime minus E, for instance. And so this is the energy difference, let's call it delta. Okay. And if the new configuration has an energy which is lower than the energy where you were, then for sure you accept the change. So your goal is to minimize the energy, right? So you accept all the changes that accomplish this task. So then you accept it with probability 1. But in contrast, if the new the configuration has an energy larger than the energy of the system where you were, then you don't reject immediately the change, but you give some probability of acceptance. Usually the probability of acceptance decreases with this energy difference delta. Okay, so if the new energy is much larger than the energy where you are, you reject the change, so the probability of acceptance is 0. But if it's a bit larger, so you will have a non-negligible chance or a relevant chance to accept it. Okay. Let's say this decay is controlled usually, so a typical acceptance function is given. Let's say that you say that you put a 1 if delta is negative. Okay, you will accept it. And here typically people use an exponential decay. Exponential decay that depends on, I use here delta and here the difference of if delta is positive. Okay, where this temperature, where this T parameter here depends the fast of this decay, and it symbolizes a kind of temperature. Okay, so at large temperatures, this decay is flatter. No? The function doesn't decay very rapidly. So this means that you allow the system to explore high energy configurations. Okay. In contrast, if it is very small, it means that this just decays so fast that you basically suppress the possibility of going to configurations that have a larger energy. Okay. And now we will understand why the origin of this name. So the idea of the algorithm is that initially you start with some sequence X, you propose randomly a new solution, X prime, and then you set the temperature to a large value, in the sense that you are simulating that your system is very hot. Okay, so it's very likely that you will explore high energy configurations. But while you are iterating this process many times, you start to decrease temperature, and with this decreasing of temperature, what you are doing is that you are limiting the possibility of exploring conversions with a larger energy. Okay, so you are in practice cooling down your system. So you will continue this process of gradually decreasing T until you reach the final. Well, at some point you have to decide when you stop, right? Usually, when you let your program running for some time and you see some convergence, when you see a convergence, you are happy and you stop, and or you explore as you continue with the computational resources that you have. The point is the following, that initially you let the system explore high energy configurations, and the idea of this is to avoid getting trapped in local minimum. So now I will put here an example of a potential, for instance, our energy landscape. Okay. But notice that this is a continuous example. It's not a discrete example like the one that we are considering, but I think it just made to visualize. So if you randomly start initially in some point here, then you would, because here there is a minimum gap, here there is a local minima, you would never explore, if you are not able to go to configurations with higher energies, you would never reach other configurations with an energy which is smaller than the one that you started with. Okay, so the idea of starting with a large temperature is precisely to allow the system to explore far away and not to get trapped in local minima. Okay, this algorithm, this simulated annealing algorithm, has some connection with the quantum annealing. The difference, as we will see later, is that when here we are kind of exploring this classically by jumping above the potentials, because we kind of give thermal fluctuations to the system, we let the energy system to increase, that this mimics these thermal fluctuations. In the quantum annealing, we will see that the idea would be that if we are here, we kind of will tunnel to other configurations. It's not that we will start in some particular place. We will see that in the quantum annealing, our original or our initial state will be completely spread on all the conversion space, and the process of annealing will be just let's say shrinking the wave function until we find the final lab state. But there is this connection between these two methods. Okay, so with this, we finish the lecture of the classical solvers. We have presented the idea of an exact solver. That the idea of exact solvers that we cover exhaustively all the conversion space, and we have seen that this is not possible to implement these exact methods when the systems and the problems are very large. And in these situations, we need to make use of heuristic methods that don't explore exhaustively all the conversion space, but just with some strategy, they just explore a fraction of it with some behavior rule that tends to bring the system towards the minimum energy configuration.